Alright, now that we have created our mesh, and we've dumped it, let's take a look at what we would do next. Okay, we want to run the thing. So in particular, one way, okay, we have used this application to generate the grid. We're going to use this wizard to actually set the problem up. In the process, we're going to launch a window and take a look at the Firefox application to look at some setup information, but let's go ahead and set this problem up. Okay, so we will go in, do the simple foam wizard. Okay, so we have to have a name, so I don't know what to call, so ABCD would be a good one. The base directory. The base directory of the study, which I like to always use, the directory in which we're in, and then we need to find the file. They don't necessarily have to be in the same place, but it's best to keep them this way. Now, one of the things I've found, and we need to be careful about this, is if there's any spaces in these names, it can blow things up. I don't know exactly why. I'm not really looking into it, but I'm sure that it has to do with a string issue, and if there's a space, the command goes off in a different particular direction. Inlet groups, I think we called it inlet, but it's whatever you called it in the ideas file. Exit is what we called the outlet. We called those walls. We don't have any symmetry condition. Now, if you remember, we had decided that the inlet flow was going to be down the Y direction. These last three, we're going to have to take a little bit of time and explain some of these. Now let's see, if I go to Open Foam, let's see, tutorial, there you go. Okay, if you go to the Open Foam tutorial, let's chapter 2 tutorial. Was that the one I wanted? Now, here we go. Yes. Let's go into the high Reynolds number case. Now, probably I'll have to wait for it to load the whole thing. Okay, so high Reynolds number flow. And I'm going to do some rough estimating. When I mean rough, I mean really rough estimations of some of the values that go in these characters by looking at some of the case down here. Think about it like this, okay? And this is very rough, but it tends to work. I don't remember the diameter of our pipe that we had coming in, but if you read through this case, we have an inlet velocity of 1. Now this could be changed to anything. As always, a Reynolds number in these cases is what dictates the flow. So you can change the geometry in any particular way. As it turns out that this new has a lot to do with the Reynolds number. You remember it's rho velocity some length over this, or the velocity some length scale over nu. Now, we'll look at this in a little bit, but let's look at the K. This is a kinetic energy, and this is the dissipation. So if you look through here, you'll see, and I would say read this, but what you find out is the kinetic energy is the fluctuating component of the velocity times itself, dotted with itself, and the average of it, and then you take half of it. So if you look at this and go down the way he set it up, he has said that he has estimated that the fluctuating component equals to about 5% of the lid velocity, or inlet, or whatever you want to call it, and that the length scale is equal to about 20% of the box width. Now, the whole goal here is to maintain consistency, not to be so accurate that you really hit it right on the mark. In other words, you need to have the K and the epsilon in such a functional relationship that they're not totally off base when it comes to these models. So this is a particular way of doing this. So if we estimate that our length scale is, say, the same as his, 0.1 meters, and we estimate that our inlet velocity is 1, then essentially our numbers would be just like his. So what he's saying is that all of these are 5/100ths of 1 meter per second, and then what he does is he puts them in here, and the reason there's a 3 here is because there's a 1, 2, and a 3 here. So it's 3/2 of 5 squared, which each one of these numbers is squared, and he gets this value. Now let's run the screen on up a little bit, and here in fact is his major key. Now that he's come up with a value for this, if you just randomly say epsilon is equal to some number, say 1, then you have a huge length scale. Or, I'm sorry, you have a reverse length scale. So you need to have these somewhat consistent. So we're going to go with his. We're going to come back and be real meticulous later on. But for right now, I'm saying my inlet is that. My length scale is about 0.1. Now the length scale has something to do with it's approximately equal to, say there's a vorticities in the flow that comes into the container or into the inlet. Then these length scales are approximately the length of the variations. As the length scale goes down smaller, the viscosity will take the kinetic energy out a lot easier. What the viscosity does to the larger length scale is break them into progressively smaller length scales, and eventually it'll take the energy out. So as long as we specify that and we maintain consistency, you take this value and put it back in here. The C mu, which down here should be about 0.9, I believe. Oh, I'm sorry, 0.09. Then you get a number out of this. So for this particular time, and this will not always be the case, but for right now, I am going to select the same values, or approximately the same values that he did in this example. 0.0375, and then 0.3765. Now let's take a look at what new is. If you look in here, let's see if I just hit a Control F and find new, and I need to go to the very top and then just hit somewhere and go to next. What you find out is, okay, and I'll move it back up a little bit, and this will give me some space to write. Okay, let's take a look at this. He specifies new. These are the dimensions of new, and if you look real close, you'll see a correlation between this and this. So this one is the exponent on the meters, or the length scale. This is the exponent on the seconds, or the time scale. So if you think about it in a generic sense, it's a length and a time, and this one's not in there, and there's several other units for consideration. What he has done is he said the inlet is at 1 meter per second. Now, if you look at it, the Reynolds number is equal to, like we said before, rho velocity length over this, or velocity length over nu. Now, he has decided, okay, where d and u are the characteristics length, he's saying that D is equal to 0.1. Now we haven't specified our D or our length yet, but when we do, we need to do it off of the geometry, and I don't remember what the diameter of the inlet was. I have no memory of that. I just made it. So the unique thing here is that I've specified that as being 1. Now I controlled the Reynolds number by changing this value, the new, and based upon what my length scale up, or not the length scale, but the length, the non-dimensionalized length number, like the diameter of the inlet pipe, and I have no memory of what that was. If I put that in as the length, then the Reynolds number will be based on that. Now how do I make a change? The easiest way to make a change here is to change this particular number. If I want Reynolds number to be higher, what do? I take that number, which remember it's on the bottom, and if I make it go down, if I make new go down, I make the Reynolds number go up. So for right now, I'm going to put in, say, 0.001. .001, and I can hit the go button. Now before I hit the go button, I'm going to get this out of the screen. Now this is a terminal that I'm going to kind of try to expand a little bit, because it will write in the Python script, will write into this. Okay, so it says a new simple foam study has been created. Please check the generated files and then run the simple foam to start the solver. I hit OK, and then it basically dumps me into this particular terminal window. Now let's take a look at some of these things. First of all, it says it sorts. Now it sorted through that ideas file. It basically told me first occurrence of element type 11. It told me several things along in here. It reading the cell, starting reading line 3, read that many points, processing tags, but suddenly I see boundary faces, and I saw that there is an inlet, there's a wall, and an exit. Now it says constructing the mesh with non-default patch size of, there aren't too many inlet patches. There are 10,000 wall patches and 150 exit patches. And it basically said that's it. And it's ready to run. Now let's see what it did to me. Let's move this to the side. We're going to keep it here, but we're going to move it to the side. I'm going to go into Home Folders, Study, and first thing you see is it created a directory that was called ABCD. I didn't know what to call the thing, so I just called it ABCD. If you look down in there, you see something interesting. You see several shell scripts. You see a post-processing shell, parallel run, and a simple run. Now this is basically where I'm going to run in a minute. I see the ideas file moved over into here. I mean, it originally was right here, but it moved it over in there. I see a routine called clean all, and what that does is after a run I can clean everything out and put it back to the original run state. Now if I go in here, I'll see, let's go through each individual ones of these. First let's go with the constants, transport properties, and what you'll see right off is, I don't know if you remember it, but there is the new that I entered, the 0.001 meters squared over second, and that's my new. I said squared, but I wrote something different. So this is the properties that he gets from there. Okay, if you look at it, you have the turbulence model is turned on. Polymesh, what you'll see is the information from, there are three, hang on, let me bring up we have three types of patches. We have the inlet, these are the names that I put in Salome. So the walls, remember those, and the exit, remember those. There are 150 of those faces. The starting face is there. There are 10,000 of those and 160 there. If you look at the faces, you'll see a whole list of all the faces. Think about what this is. This is the node number that occupies three faces. So in other words, this is the node number 3621, 3616, and 15088. That makes a triangle. If you think about it, that's essentially what you're doing. It's picked 3 points and it made a triangle out of it. So this is a particular face. It just so happened that this is 3621 node, 3616 node, and 15088. That designates a patch there. Not that important to you, but it is the faces, and if you just go through here, you'll see tons of faces all the way through here. Neighbors. Now these are the face neighbors. You don't really, this is what's generated from that. Owner points, these are all the physical points. You start seeing coordinates, X, Y, and Z coordinates here all the way through. So in other words, if you want to know the node, okay, there are 16,000 plus nodes. Here's the first node, here's the second node, here's the third node, here's the fourth node, so on and so forth. And those are the constants. Okay, the initial conditions are listed here. Let's take a look at this. If you remember, I don't know if your memory is that long, but look, we initialize it at a uniform value, the 3750. If you want to see that, that is essentially the value that was put down in here. I'd have to go back and find it, but I think it wouldn't be that hard. There was the 3750 right there. And then you got a uniform, the walls are uniform, the inlet's uniform. Let's see, what else do you have? I have epsilon, which I put that in, and that's the 765. If you look back here, there it is, 765. What else do you have? I actually have the velocity. And you notice that's meters per second. They have a uniform value on the inlet, which is this. The rest of these I'm not going to pay too much attention to. Next we're going to pay attention to this one. Of all the ones that we probably will change, it's this one. It's what the type of application. We're mostly going to use this all the time anyway. We have the end time, the time that this thing, it's essentially a time stepping routine that's not time accurate, but it does get you to the steady state solution. You can make it time accurate by using a different one. We're going to stop the simulation at, hang on, we're going to stop the simulation at 100 seconds. Our delta t is going to be 1 second. We're going to write a solution every 10 seconds. And the rest of these we're not going to pay too much attention to, but these are the type of solvers that are used in some of the relaxation factors and some of the factors. This is generally will be set up for you, so you don't have to worry about a lot of this. And this is if you want to, well, this is a, here we'll come back and we can, if you want to run it in a parallel machine, you got number of processors is 4, simple foam and parallel. So this is how you would run the thing in You would decompose the problem. We're just going to run it using this, just simple foam. So with that in mind, we're going to go back here. We don't know exactly where this left us, so let's do present working directory, and it didn't leave us there. So list, and we're going to move into ST, and I can hit the tab key to fill this out. Hit the tab key again, it fills it out again. LL is a long list. Now I can hit this. You have to hit a dot and a slash and hit that. I always hit a tab and it will complete it for me. And I'm going to hit run. And what it's doing is it's running the solution. And what I'm going to do is, since we've already run this 20 minutes into this video, I'm going to stop the video and pick it up at the end of the solution cycle.